Hello everyone, myself Anugraha Ganesh DG from first MSc Physics, Hindustan College of Arts and Science, Coimbatore. Today we are going to discuss about the topics transition probabilities and selection rules for dipole radiation. So firstly, let's see what is transition probability. As a factor, KERA-N is a component of KER-N in the polarization direction. Then let's take the modulus of that part and on squaring it, we get the equation modulus KER-N square cos square theta, where theta is the angle between the direction of polarization and KER-N. Since the radiation is isotrope, this term is not restricted to a single plane as assumed. So, taking it in all direction, let's consider the equation as KERA-N whole square is equal to 1 by 3 KER-N the whole square is equal to 1 by 3 mu Kn square, where mu Kn is equal to KER-N. The probability that H dash has induced a transition from state N to state K is given by modulus Ck square. Substituting the value of Hkn dash of t on previously obtained equation and the corresponding terms become Ck dash of t is equal to minus omega Kn divided by Ch cut KERA-N integral A0 of omega d omega integral 0 to t exponential I into omega Kn minus omega t dash into dt dash. Then we can simplify, and on taking the square of this term, we get Ck dash of t the whole square is equal to 4 omega Kn square divided by 3 C square H cut square mu Kn square integral modulus of A0 of omega square sine square omega Kn minus omega into t divided by 2 the whole divided by omega Kn minus omega square d omega. Now let's replace KERA-N the whole square by this term. The factor A0 omega the whole square is fairly broad and the remaining factor in the integral is sharply peaked about omega is equal to omega Kn. Therefore, we may replace this term by A0 omega Kn the whole square and take it outside the integral. So, let's evaluate the integral. The variable of integration may be changed from omega to x defined by x is equal to omega minus omega Kn into t divided by 2. Then we get the expression Ck dash of t the whole square is equal to 2t divided by 3h square into mu Kn square rho of omega Kn integral minus infinity to infinity sine square x divided by x square into dx. Now let's replace the value of A0 omega Kn square, and the value of integration is pi, and the probability per unit time for absorption becomes omega is equal to 2 pi divided by 3h square modulus mu Kn the whole square rho of omega Kn. The term representing emission has a large value when omega Kn plus omega is equal to 0 or Ek is equal to En minus h omega. Then evaluation of the transition probability leads to the same result as that for absorption. In the emission process, the electromagnetic field gains energy h omega from the atom or molecule, and therefore in the output we have 2 photons. Hence, at thermal equilibrium, if omega is very much less than kT divided by h, the number of stimulated emissions far exceeds the number of spontaneous emissions, whereas reverse is the situation if omega is very much greater than kT divided by h. So next, let's see what is selection rules. Calculation of transition probabilities for absorption, stimulated emission and spontaneous emission has been reduced to the evaluation of transition's dipole moment. So we have the equation mu Kn is equal to psi k mu psi n, where mu is equal to minus Er. Transition between all the states are not allowed. Therefore, the selection rules specify the transition that may occur on the basis of dipole approximation. The transition dipole moment is non-zero are allowed transitions, and those for which it is 0 are forbidden transitions. Transition dipole moment can be considered as a measure of imbalance created in the electromagnetic field when the electron makes a transition between states. We have already seen the parity of atomic orbit with quantum number L is equal to minus 1 the whole raised to L. The S and D orbits have even parity, whereas P and F orbitals have odd parity. The parity of integrand of the transition dipole moment mu kn is minus 1 the whole raised to L k into minus 1 the whole raised to Ln is equal to minus 1 the whole raised to Lk plus Ln plus 1, which is even. If the two orbitals have opposite parity and odd, if they have the same parity, group theoretical considerations suggest that a transition dipole moment will be finite only when the integrand is totally symmetric under symmetric operation of the system. Therefore, only allowed electronic dipole transition are those involving a change in parity. This is called Laporte selection rule. For a hydrogenic atoms, we may specify the states by the usual quantum numbers n, l and m. For a transition to be allowed, the dipole moment matrix element n dash, l dash, m dash, r, n, l, m must be finite. On the basis of Laporte selection rule, L dash minus L is equal to delta L, which is equal to plus or minus L. To obtain the selection rule on the quantum number m, we may write the matrix element as n dash L dash m dash r n l m, which is equal to I cap into n dash L dash m dash x n l m plus j cap n dash L dash m dash y n l m plus k cap n dash L dash m dash z n l m. If the radiation is plane polarized with the electric field in the z direction, the z component of the dipole moment is the only relevant quantity, which is given by n dash L dash m dash r cos theta n l m. The phi part of this integral is equal to integral 0 to 2 pi exponential I m minus m dash into phi d phi, which is equal to finite term. Finite only when m dash is equal to m or delta m is equal to 0. If the radiation is polarized in the xy plane, we have to calculate the matrix elements of x and y. However, it is found convenient to evaluate the matrix elements of x plus or minus iy. Since it is always possible to get the values corresponding to x and y by the relation x is equal to half into x plus iy plus x minus iy. Y is equal to 1 by 2i into x plus iy minus x minus iy. In polar coordinates, x plus or minus iy is equal to r sin theta cos phi plus or minus ir sin theta sin phi, which is equal to r sin theta exponential plus or minus I phi. Now the matrix elements of x plus or minus iy is n dash L dash m dash r sin theta exponential plus or minus I phi n L m, which is equal to f of r theta integral 0 to 2 pi exponential I of m minus m dash plus or minus 1 into phi, which is of d phi. The phi part is non-vanishing only when m dash minus m is equal to delta m is equal to plus or minus 1. Therefore, the arbitrary polarization, the general selection rule is delta m is equal to 0 plus or minus 1. And also we know that delta L is equal to plus or minus 1, and we conclude both the terms. Delta L is equal to plus or minus 1, delta M is equal to 0 or plus or minus 1. The origin of the selection rule delta L is equal to plus or minus 1 may be linked to the spin angular momentum of photon, which is equal to 1. When a photon is emitted or absorbed, to conserve the total angular momentum, the orbital angular momentum of the electron in the atom changes by plus or minus 1. An absorption or emission of a photon may increase the orbital angular momentum of the electron. Delta L is equal to plus 1 depending on the orientation of the electron's angular momentum with the angular momentum of the photon. The selection rules we have discussed are valid only for dipole transitions. The magnetic component of the electromagnetic field can interact with the magnetic moment of the electron in the way and induce the magnetic dipole transitions. Such transitions are 10 raised to 5 times weaker than those allowed under electric dipole transitions. As the selection rules for these transitions are different, transitions were forbidden under one category may active in other. Another type of transition in the electric quadrupole transitions wherein the spatial variation of the electric field interacts with the electric quadrupole moment. The selection rule for such transitions are delta L is equal to 0 plus or minus 2. These transitions are 10 raised to 8 times weaker than the electric dipole transition. So that's all about selection rule. So far we have discussed about transition probabilities and selection rule for dipole radiation. So these are the main content that we have to mainly focus on, and I hope you have understood the topic that we have so far discussed. Thank you.